In the last section, we talked about radical stability and radical halogenation reactions. We can also use radicals to do several other kinds of reactions that are more traditional to perform with traditional reaction sets. It's important to remember, though, that this is fairly difficult to accomplish these reactions selectively in complex molecules. The radicals are pretty unselective. The first reaction we'll add today is a radical addition to an alkene. This is an interesting reaction because it installs a halogen at the less substituted position of a double bond. With non-radical reactions, or in complex molecules, this transformation would need to be accomplished instead by a hydroboration oxidation, like BH3 and then peroxide, and then follow that with PBr3 to convert the alcohol to bromine. The peroxide in this reaction is a radical initiator by homolysis, because the OO bond is very weak. The peroxide radical quickly pulls off a hydrogen by bimolecular homolytic substitution and leaves behind a bromine radical. That bromine radical can add to an alkene, but it will add so that the radical that it forms is on the more stable side. This is possible because the bromine isn't acting as a nucleophile in this case, but is acting instead as a radical. The resulting secondary radical will be able to pull off a hydrogen radical and produce a bromine radical from HBr and keep on reacting. Again, it's easy to think of these reactions as linear, but the initiation needs to happen fairly seldomly to get the reaction to occur. After the initial bromide radical is formed, propagation steps keep the reaction going until the uncommon terminations occur. Looking at this overall mechanism, what order do you think the reactants need to be added in? Radicals are always planar. The unpaired radical electron sits in a p orbital, which allows all the other paired electrons to have lower energy. This means that radicals will have the same lack of stereo control that we see in reactions involving carbocations. So if any sort of stereo control is needed, radical reactions are not a very good choice. Some of the most interesting reactions involving radical mechanisms are the dissolving metal reductions, where an alkali metal, typically sodium or lithium, are dissolved, typically in liquid ammonium at low temperature. When the alkali metal dissolves, it releases a free solvated electron. The result is a really visually stunning, brilliant blue color that eventually turns almost gold. These solutions allow us to deliver single electrons at a time for reductions. One possible reaction with that dissolved electron is the reduction of an alkyne to an alkene. We also did reductions by poison catalysts to convert alkynes to alkenes in Chapter 19. Note the difference here. This reaction gives a transalkene instead of the cisalkene. The free electrons will go into the lowest energy unoccupied molecular orbital. In this case, it's going to be the alkyne pi antibinding orbital. When this occurs, the bond order is reduced to 2.5 and the most stable form of the double bond is formed. This moves out a lone pair, which picks up a proton and leaves behind a radical. That radical has an even lower energy as an sp2 vacancy in what we call a SOMO, a singly occupied molecular orbital, which is readily filled by other solvated electrons. The lone pair that's formed is very basic and can pick up another proton. Since the alkyne has lower energy LUMO orbitals, this reaction will react all the alkyne before the alkene reacts. We can also reduce an aromatic this way. Notice the reduction is fairly mild and gives us the unconjugated product. Again, the reactivity can be explained by the electron entering the lowest energy unoccupied molecular orbital. In this case, one of the pi molecular orbitals. Again, this reduces the bond order and frees up basic electrons. After the aromatic is broken, the lowest energy singly occupied molecular orbital, again the SOMO, is the sp2 orbital with a single electron, which is readily filled. There are 3 resonance forms, but the one with the negative charge between the two alkenes is the most stable and holds the most negative charge and therefore determines the type of product that's formed. Radical reactions are typically limited to early steps in synthesis, but certain structures tend to be good indicators of possible radical reactions. Functional groups alpha to an alkene often can come from allylic brominations like we did with NBS at the end of the last section. So this can be an indicator that a radical could have been used to form the product. Another indicator is anti-Markovnikov regiochemistry. Again, this is not the only way to form anti-Markovnikov products, but it is fewer steps and works well for simple molecules. Notice in this scheme, the last arrow also represents a radical reaction. Installing halogens on benzyl positions is one of the more straightforward forms of a radical halogenation. And of course, some transformations, like alkynes to transalkenes, truly are limited to this type of reaction mechanism. That's really the main way that you can do this. As usual, this last summary slide is included for you to peruse at your leisure in conjunction with the tables at the end of the chapter in your text.